and we scale it by a constant. And you can see that this layer actually just has 40 lines. There's some initialization stuff. This is Lua, by the way, if this is looking some foreign to you. But there's initialization, where you actually pass in that A that you want to use as your scaling. And then during the forward pass, which they call update output, in a forward pass, all they do is they just multiply AX and return it. And in the backward pass, which they call update grad input, there's an if statement here. But really, when you look at these 3 lines that are most important, you can see that all it's doing is it's copying into a variable grad input, which it needs to compute. That's your gradient that you're passing up. The grad input is, you're copying grad output. Grad output is your gradient on the final loss. You're copying that over into grad input, and you're multiplying by the scalar, which is what you should be doing, because your local gradient is just A, and so you take the output you take the gradient from above, and you just scale it by A, which is what these 3 lines are doing. And that's your grad input, and that's what you return. So that's one of the hundreds of layers that are in Torch. We can also look at examples in Caffe. Caffe is also a deep learning framework specifically for images that you might be working with. Again, if you go into the layers directory in GitHub, you just see all these layers. All of them implement the forward-backward API. So just to give you an example, there's a sigmoid layer in Caffe. So sigmoid layer takes a blob. So Caffe likes to call these tensors blobs. So it takes a blob, it's just an n-dimensional array of numbers, and it passes it element-wise through a sigmoid function. And so it's computing in the forward pass a sigmoid, which you can see there. Let me use my pointer. OK, so there it's calling. So a lot of this stuff is just boilerplate, getting pointers to all the data. And then we have a bottom blob, and we're calling a sigmoid function on the bottom. And that's just the sigmoid function right there. So that's what we compute. And in the backward pass, some boilerplate stuff. But really what's important is we need to compute the gradient times the chain rule here. So that's what you see in this line. That's where the magic happens, where we take the diff. So they call the gradients diffs. And you compute the bottom diff is the top diff times this piece, which is really that's the local gradient. So this is chain rule happening right here through that multiplication. So, and that's it. And so every single layer, just the forward-backward API. And then you have a computational graph on top, or a net object that keeps track of all the connectivity. OK, any questions about some of these implementations and so on? Go ahead.
So do we have to go through the entire forward and backward step for every update?
Yes, thank you. So the question is, do you have to go through forward and backward for every update? The answer is yes, because when you want to do update, you need the gradient. And so you need to do forward on you sample a mini batch, you do a forward, you right away do a backward, and now you have your analytic gradient. And now I can do an update, where I take my analytic gradient and I change my weights a tiny bit in the direction, the negative direction of your gradient. So forward computes the loss, backward computes your gradient, and then the update uses the gradient to increment your weights a bit. So that's what keeps happening in the loop. When you train a neural network, that's all that's happening. Forward, backward, update, forward, backward, update. We'll see that in a bit. Go ahead.
The reason for having for loop there is simply because this is a vector format.
You're asking about the for loop.
In the backward red box.
Oh, is there a for loop here? I didn't even notice. OK. Yeah, they have a for loop. Yeah, so you'd like this to be vectorized. I'm not actually sure. Oh, because this is C++. So I think, yeah, they just do it. Go for it.
if you have CPU only. So.
Yeah. So this is a CPU implementation, by the way. I should mention that this is a CPU implementation of the sigmoid layer. There's a second file that implements the sigmoid layer on GPU, and that's CUDA code. And so that's a separate file. It would be sigmoid.cu or something like that. I'm not showing you that. Any other questions? OK, great. So one point I'd like to make is we'll be, of course, working with vectors. So these things flowing along our graphs are not just scalars. They're going to be entire vectors. And so nothing changes. The only thing that is different now, since these are vectors, x, y, and z are vectors, is that this local gradient, which before used to be just a scalar, now they're in general, for general expressions, they're full Jacobian matrices. And so Jacobian matrix is this two-dimensional matrix, and basically tells you what is the influence of every single element in x on every single element of z. And that's what Jacobian matrix stores. And the gradient is the same expression as before, but now, say here, dz by dx is a vector, and dl by dz dl by dz is a vector, and dz by dx is an entire Jacobian matrix. So you end up with an entire matrix vector multiply to actually chain the gradient backwards.
If you only have one output, do you still have two-dimensional gradient as you go backward?
No. So I'll come back to this point in a bit. You never actually end up forming the full Jacobian. You'll never actually do this matrix multiply most of the time. This is just a general way of looking at arbitrary function, and I need to keep track of this. And I think that these two are actually out of order because dz by dx is the Jacobian, which should be on the left side. So I think that's a mistake in the slide because this should be a matrix vector multiply. So I'll show you why you don't actually need to ever form those Jacobians. So let's work with a specific example that is relatively common in neural networks. Suppose we have this nonlinearity, max of 0 and x. So really what this operation is doing is it's receiving a vector, say of 4096 numbers, which is a typical thing you might want to do. 4096 numbers, real valued, come in. And you're computing an element-wise thresholding at 0. So anything that is lower than 0 gets clamped to 0. And that's your function that you're computing. And so output vector is of the same dimension. So the question here I'd like to ask is, what is the size of the Jacobian matrix for this layer? (4096 by 4096). In principle, every single number in here could have influenced every single number in there. But that's not the case necessarily, right? So the second question is, so this is a huge matrix, 16 million numbers. But why would you never form it? What does the Jacobian actually look like?
Wouldn't it, because it's element-wise, wouldn't it be a vector?
No, Jacobian will always be a matrix. Because every one of these 4096 could have influenced every...
I thought you said it's element-wise.
It is. So the Jacobian is still a giant 4096 by 4096 matrix, but it has special structure, right? And what is that special structure? Good.
It's diagonal, and some are even zeros.
Yeah. So this Jacobian is huge. So it's 4096 by 4096 matrix. But there's only elements on the diagonal because this is an element-wise operation. And moreover, they're not just ones, but for whichever element was less than 0, it was clamped to 0. So some of these ones actually are zeros in whichever elements had a lower than 0 value during the forward pass. And so the Jacobian would just be almost an identity matrix, but some of them are actually 0. Okay, so you never actually would want to form the full Jacobian because that's silly. And so you never actually want to carry out this operation as a matrix vector multiply because there's special structure that we want to take advantage of. And so in particular, the gradient, the backward pass for this operation is very, very easy because you just want to look at all the dimensions where your input was less than 0, and you want to kill the gradient in those dimensions. You want to set the gradient to 0 in those dimensions. So you take the grad output here, and whichever numbers were less than 0, you just set them to 0. Set those gradients to 0, and then you continue backward pass. So very simple operations in the end in terms of efficiency.
In the backward pass, you always just report back a vector for each of the inputs.
That's right.
You never actually, you could do a matrix if you needed to in your internal state, but when you actually report back, you're always just a vector.
Yeah. So the question is, the communication between the gates is always just vectors. That's right. So this Jacobian, if you wanted to, you can form that, but that's internal to you inside the gate. And you can use that to do backprop, but what's going back to other gates, they only care about the gradient vector.
Unless you wind up having multiple outputs overall in your entire network.
Yes. So the question is, unless you end up having multiple outputs, because then for each output we have to do this, and so yeah. So we'll never actually run into that case because we almost always have a single output, scalar valued at the end, because we're interested in loss functions. So we just have a single number at the end that we're interested in computing gradients with respect to. If we had multiple outputs, then we have to keep track of all of those as well in parallel when we do the backpropagation. But we just have scalar valued loss functions, so we don't have to worry about that. Okay, makes sense? So I wanted to also make the point that actually 4096 dimension is not even crazy. Usually we use mini batches, so say a mini batch of 100 elements going through at the same time, and then you'd end up with 100 4096 dimensional vectors that are all coming in parallel. But all the examples in a mini batch are processed independently of each other in parallel, and so this Jacobian matrix really ends up being 400,000 by 400,000, so huge. So you never form these basically, and you take care to actually take advantage of the sparsity structure in that Jacobian, and you hand code operations. You don't actually write the fully generalized chain rule inside any gate implementation. Okay, cool. So I'd like to point out that in your assignment, you'll be writing SVMs and softmax and so on. And I just kind of wanted to give you a hint on the design of how you actually should approach this problem. What you should do is just think about it as a backpropagation, even if you're doing this linear classification optimization. So roughly, your structure should look something like this, where, again, stage your computation in units that you know the local gradient of, and then do backprop when you actually evaluate these gradients in your assignment. So in the top, your code will look something like this, where we don't have any graph structure because you're doing everything inline, so no crazy edges or anything like that that you have to do. You will do that in the second assignment. You'll actually come up with a graph object, and you'll implement your layers. But in the first assignment, you're just doing it inline, just straight up vanilla setup. And so compute your scores based on W and X. Compute these margins, which are max of 0 and the score differences. Compute the loss, and then do backprop. And in particular, I would really advise you to have this intermediate scores that you create. It's a matrix. And then compute the gradient on scores before you compute the gradient on your weights. And so use chain rule here. Otherwise, you might be tempted to try to just derive W, the gradient on W equals, and then implement that. And that's an unhealthy way of approaching the problem. So stage your computation and do backprop through this scores, and that will help you out. OK, cool. So let's see, the summary so far. Neural networks are hopelessly large, so we end up with these computational structures and these intermediate nodes. Forward, backward API for both the nodes and also for the graph structure. And the graph structure is usually a very thin wrapper around all these layers, and it handles all the communication between them. And this communication is always along like vectors being passed around. In practice, when we write these implementations, what we're passing around are these n-dimensional tensors. Really what that means is just an n-dimensional array, so like a NumPy array. Those are what goes between the gates. And then internally, every single gate knows what to do in the forward and the backward pass. OK, so at this point, I'm going to end with backpropagation, and I'm going to go into neural networks. So any questions before we move on from backprop? Go ahead.
Yeah, in the last slide, the summation symbol, is that sort of handled with the fact that we're using matrices instead of vectors? Or how is the summation symbol?
The summation inside li equals blah?
Yeah.
Yeah, so there's a sum there. So you'd want that to be a vectorized operation that you... Oh, yeah, so basically the challenge in your assignment almost is how do you make sure that you do all of this efficiently, nicely with matrix vector operations in NumPy? So that's going to be some of the brain teaser stuff that you guys are going to have to do.
So you wouldn't implement a gate for that. You would make that implicit in the structure of the variables.
Yeah, so it's up to you what you want your gates to be like and what you want them to be.
But that wouldn't be one big plus gate, right?
Yeah, I don't think you'd want to do that. Yeah, I'm not sure. Maybe that works. I don't know. But yeah, it's up to you to design this and to backprop through it. Yeah, so that's fun. OK, so we're going to go to neural networks. This is exactly what they look like. So you'll be implementing these. And this is just what happens when you search on Google Images for neural networks. This is, I think, the first result or something like that. So let's look at neural networks. And before we dive into neural networks, actually, I'd like to do it first without all the brain stuff. So forget that they're neural, forget that they have any relation whatsoever to a brain. They don't, but forget if you thought that they did, that they do. Let's just look at score functions, where before we saw that f equals wx is what we've been working with so far. But now, as I said, we're going to start to make that f more complex. And so if you wanted to use a neural network, then you're going to change that equation to this. So this is a 2-layer neural network, and that's what it looks like. And it's just a more complex mathematical expression of x. And so what's happening here is you receive your input x, and you multiply it by a matrix, just like we did before. Now what comes next is a nonlinearity, or activation function. And we're going to go into several choices that you might make for these. In this case, I'm using the thresholding at 0 as an activation function. So basically, we're doing matrix multiply. We threshold everything negative to 0. And then we do one more matrix multiply. And that gives us our scores. And so if I was to draw this, say in case of CFAR10, we have 3,072 numbers going in. Those are the pixel values. And before, we just went one single matrix multiply to scores. We went right away to 10 numbers. But now we get to go through this intermediate representation of a hidden state. We'll call them hidden layers. So a hidden vector h of 100 numbers, say, or whatever you want your size of your neural network to be. So this is a hyperparameter that's, say, 100. And we go through this intermediate representation. So matrix multiply gives us 100 numbers, threshold at 0, and then one more matrix multiply to get the scores. And since we have more numbers, we have more wiggle to do more interesting things. So one particular example of something interesting you might think that a neural network could do is going back to this example of interpreting linear classifiers on CFAR10, and we saw that the car class has this red car that tries to merge all the modes of different cars facing different directions. And so in this case, one single linear classifier had to go across all those modes, and we couldn't deal with, for example, cars of different colors. That wasn't very natural to do. But now we have 100 numbers in this intermediate, and so you might imagine, for example, that one of those numbers could be just picking up on red car facing forward. It's just classifying, is there a red car facing forward? Another one could be red car facing slightly to the left, left car facing slightly to the right. And those elements of H would only become positive if they find that thing in the image. Otherwise, they stay at 0. And so another H might look for green cars or yellow cars or whatever else in different orientations. So now we can have a template for all these different modes. And so these neurons turn on or off if they find the thing they're looking for, a car of some specific type. And then this W2 matrix can sum across all those little car templates. So now we have, like, say, 20 car templates of what cars could look like. And now to compute the score of car classifier, there's an additional matrix multiply, so we have a choice of doing a weighted sum over them. And so if any one of them turn on, then through my weighted sum with positive weights, presumably, I would be adding up and getting a higher score. And so now I can have this multimodal car classifier through this additional hidden layer in between there. So that's hand-wavy reason for why these would do something more interesting. Was there a question? Yeah.
So let's say the edge layer has less than 10 units. Would it then be always inferior than just using a linear classifier?
So the question is, if H had less than 10 units, would it be inferior to a linear classifier? I think that's actually not obvious to me. It's an interesting question. I think you could make that work. I think you could make it work. Yeah, I think that would actually work. Someone should try that for extra points in the assignment. So you'll have a section on the assignment, do something fun or extra. And so you get to come up with whatever you think is interesting experiment, and we'll give you some bonus points. So that's a good candidate for something you might want to investigate, whether that works or not. Any other questions? Good.
So are there 100 of those car-facing left, car-facing right sorts of features per class, per each of the 10 classes, or is it for all of the classes?
Sorry, I don't think I understood the question.
So you said there might be certain elements in the H vector
Yep.
that represent certain things, like the car facing left or facing right.
Yep.
Do each of the 10 classes have 100 different
I see.
of those things? Or?
So you're really asking about the layout of the H vector and how it gets allocated over the different modes of the data set. And I don't have a good answer for that. Since we're going to train this fully with backpropagation, I think it's slightly naive to think that there will be exact template for, say, a red car facing left. You probably won't find that. You'll find these kind of like mixes and weird things, intermediates, and so on. So this neural network will come in and it will optimally find a way to truncate your data with its linear boundaries, and these weights will all get adjusted just to make it come out right. So it's really hard to say. We'll be kind of tangled up, I think. Go ahead.
I had a mistake, but so the number 100 for H was like chosen arbitrarily.
That's right. So that's the size of a hidden layer, and that's a hyperparameter. We get to choose that. So I chose 100. Usually that's going to be, you'll see that with neural networks, we'll go into this a lot, but usually you want them to be as big as possible as it fits in your computer and so on. So more is better, but we'll go into that. Good.
Is it always the max of 0 and H, or?
So you're asking, do we always take max of 0 and H? And we don't, and it's like 5 slides away.
Oh.
So I'm going to go into neural networks. I guess maybe I should preemptively just go ahead and then take questions near the end. If you wanted this to be a 3-layer neural network, by the way, there's a very simple way in which we just extend this, right? So we just keep continuing the same pattern where we have all these intermediate hidden nodes, and then we can keep making our network deeper and deeper, and you can compute more interesting functions because you're giving yourself more time to compute something interesting in a hand-wavy way. Now, one other slide I wanted to flash is that training a 2-layer neural network, is actually quite simple when it comes down to it. So this is a slide borrowed from a blog post I found. And basically, it suffices roughly 11 lines of Python to implement a 2-layer neural network doing binary classification on, what is this, 2-dimensional data. So you have a two-dimensional data matrix, X. You have, sorry, it's three-dimensional. And you have binary labels for Y. And then sin 0, sin 1 are your weight matrices, weight 1, weight 2. And so I think they're called sin for synapse, but I'm not sure. And then this is the optimization loop here. And what you're seeing here, I should use my pointer more. What you're seeing here is we're computing the first layer activations, but this is using a sigmoid nonlinearity, not a max of 0 and x. And we'll go into a bit of what these nonlinearities might be. So sigmoid is one form, is computing the first layer, and then it's computing second layer, and then it's computing here right away the backward pass. So this is the L2 delta is the gradient on L2, the gradient on L1, and the gradient, and this is a matrix, is an update here. So right away he's doing an update at the same time as doing the final piece of backprop here, where he's formulating the gradient on the W, and right away he's adding to gradient here. And so really 11 lines suffice to train a neural network to do binary classification. The reason that this loss might look slightly different from what you've seen right now is that this is a logistic regression loss. So you saw a generalization of it, which is the softmax classifier into multiple dimensions. But this is basically a logistic loss being updated here. And you can go through this in more detail by yourself. But the logistic regression loss looks slightly different. And that's inside there. But otherwise, yeah, so this is not too crazy of a computation. And very few lines of code suffice to actually train these networks. Everything else is fluff. How do you make it efficient? How do you, there's a cross-validation pipeline that you need to have, and all this stuff that goes on top to actually give these large code bases. But the kernel of it is quite simple. We compute these layers, do forward pass, we do backward pass, we do an update. We keep iterating this over and over again. Good.
What's that random function?
The random function is creating your first initial random weights. So you need to start somewhere. So you generate a random W. OK. Now I wanted to mention that you'll also be training a two-layer neural network in this class. So you'll be doing something very similar to this, but you're not using logistic regression, and you might have different activation functions. But again, just my advice to you when you implement this is stage your computation into these intermediate results, and then do proper backpropagation into every intermediate result. So you might have, you compute your, let's see. You receive these weight matrices and also the biases. I don't believe you have biases actually in your SVM and in your softmax, but here you'll have biases. So take your weight matrices and the biases, compute the first hidden layer, compute your scores, compute your loss, and then do backward pass. So backprop into scores, then backprop into the weights at the second layer, and backprop into this H1 vector, and then through H1 backprop into the first weight matrices and the first biases. Okay, so do proper backpropagation here. Otherwise, if you try to right away just say, what is dW1? What is the gradient on W1? If you just try to make a single expression for it, it will be way too large and you'll have headaches. So do it through a series of steps in backpropagation. Okay, that's just a hint. Okay, so now I'd like to, so that was the presentation of neural networks without all the brain stuff. And so it looks fairly simple. So now we're going to make it slightly more insane by folding in all kinds of like motivations, mostly historical about like how this came about, that it's related to brain at all. And so we have neural networks and we have neurons inside these neural networks. So this is what neurons look like. This is just what happens when you search on image search neurons. So there you go. Now your actual biological neurons don't look like this, unfortunately. They actually look more like that. And so a neuron, just very briefly, just to give you an idea about where this is all coming from. You have the cell body, or a soma as people like to call it, and it's got all these dendrites that are connected to other neurons. So there's a cluster of other neurons and cell bodies over here. And dendrites are really these appendages that listen to them. So this is your inputs to a neuron, and then it's got a single axon that comes out of a neuron that carries the output of the computation that this neuron performs. So usually you have this neuron that receives inputs. If many of them align, then this cell, this neuron can choose to spike. It sends an activation potential down the axon, and then this actually like diverges out to connect to dendrites of other neurons that are downstream. So there are other neurons here, and their dendrites connect to the axons of these guys. So basically just neurons connected through these synapses in between. And we have these dendrites that are the input to a neuron, and this axon that actually carries the output of a neuron. And so basically you can come up with a very crude model of a neuron, and it will look something like this. We have an axon. So this is the cell body here of a neuron. And just imagine an axon coming from a different neuron somewhere in the network. And this neuron is connected to that neuron through this synapse. And every one of these synapses has a weight associated with it of how much this neuron likes that neuron, basically. And so axon carries this X, it interacts in the synapse, and they multiply in this crude model. So you get W0, X0 flowing to the soma. And then that happens for many neurons, so you have lots of inputs of W times X flowing in. And the cell body here, it just performs a sum offset by a bias. And then if an activation function is met here, so it passes it through an activation function to actually compute the output of this axon. Now, in biological models, historically, people liked to use the sigmoid nonlinearity to actually use for the activation function. The reason for that is because you get a number between 0 and 1, and you can interpret that as the rate at which this neuron is firing for that particular input. So it's a rate between 0 and 1 that's going through the activation function. So if this neuron is seeing something it likes in the neurons that connect to it, it will start to spike a lot, and the rate is described by f of the input. Okay, so that's the crude model of the neuron. If I wanted to implement this, it would look something like this. So a neuron tick function, forward pass, it receives some inputs. This is a vector. And we form a sum at the cell body, so just a linear sum. And we compute the firing rate as a sigmoid of the cell body sum and return the firing rate. And then this can plug into different neurons, right? So you can actually see that this looks very similar to a linear classifier, right? We're forming a linear sum here, a weighted sum, and we're passing that through nonlinearity. So every single neuron in this model is really like a small linear classifier, but these linear classifiers plug into each other, and they can work together to do interesting things. Now, one note to make about neurons is that they're not like biological neurons. Biological neurons are super complex. So if you go around and you start saying that neural networks work like brain, people are starting to frown. People will start to frown at you. And that's because neurons are complex dynamical systems. There are many different types of neurons. They function differently. These dendrites, they can perform lots of interesting computation. A good review article is dendrite computation, which I really enjoyed. These synapses are complex dynamical systems. They're not just a single weight. And we're not really sure if the brain uses rate code to communicate. So very crude mathematical model, and don't push this analogy too much. But it's good for kind of like media articles. And so I suppose that's why this keeps coming up again and again, is we explain that this works like your brain. But OK, I'm not going to go too deep into this. To go back to a question that was asked before, there's an entire set of nonlinearities that we can choose from. So historically, sigmoid has been used quite a bit, and we're going to go into much more detail over what these nonlinearities are, what are their trade-offs, and why you might want to use one or the other. But for now, I'd just like to flash them and mention that there are many things to choose from. Historically, people use sigmoid at 10H. As of 2012, ReLU became quite popular. It makes your networks converge quite a bit faster. So right now, if you wanted a default choice for nonlinearity, use ReLU. That's the current default recommendation. And then there's a few kind of hipster activation functions here. And so leaky ReLUs were proposed a few years ago. Max out is interesting. Very recently, ILU. And so you can come up with different activation functions, and you can describe why these might work better or not. And so this is an active area of research, is trying to come up with these activation functions that have better properties in one way or another. So we're going to go into this much more detail soon in the class. But for now, we have these neurons. We have a choice of activation function. And then we arrange these neurons into neural networks, right? So we just connect them together so they can talk to each other. And so here's an example of a 2-layer neural net or a 3-layer neural net. When you want to count the number of layers in a neural net, you count the number of layers that have weights. So here the input layer does not count as a layer because these neurons are just single values. They don't actually do any computation. So we have 2 layers here that have weights. So it's a 2-layer net. And we call these layers fully connected layers. And so remember that I've shown you that a single neuron computes this little weighted sum and then passes that through nonlinearity. In a neural network, the reason we arrange these into layers is because arranging them into layers allows us to perform the computation much more efficiently. So instead of having an amorphous blob of neurons and every one of them has to be computed independently, having them in layers allows us to use vectorized operations. And so we can compute an entire set of neurons in a single hidden layer as just at a single time as a matrix multiply. And that's why we arrange them in these layers, where neurons inside a layer can be evaluated completely in parallel, and they all see the same input. So it's a computational trick to arrange them in layers. So this is a 3-layer neural net, and this is how you would compute it. Just a bunch of matrix multiplies followed by a activation function. So now I'd like to show you a demo of how these neural networks work. So this is a JavaScript demo that I'll show you in a bit. But basically, this is an example of a 2-layer neural network doing a binary classification task. So we have 2 classes, red and green. And so we have these points in 2 dimensions. And I'm drawing the decision boundaries by the neural network. And so what you can see is when I train a neural network on this data, the more hidden neurons I have in my hidden layer, the more wiggle your neural network has, right? The more it can compute crazy functions. And just to show you effect also of regularization strength. So this is the regularization of how much you penalize large W's. So you can see that when you insist that your W's are very small, you end up with very smooth functions. So they don't have as much variance. So these neural networks, there's not as much wiggle that they can give you. And then as you decrease the regularization, these neural networks can do more and more complex tasks. So they can kind of get in and get these little squeezed out points to cover them in the training data. So let me show you what this looks like during training. OK. So there's some stuff to explain here. Let me first actually, hold on. So you can play with this because it's all in JavaScript. OK. All right. So what we're doing here is we have 6 neurons. And this is a binary classification data set with circle data. And so we have a little cluster of green dots separated by red dots. And we're training a neural network to classify this data set. So if I restart the neural network, it just starts off with a random W, and then it converges the decision boundary to actually classify the data. What I'm showing on the right, which is the cool part of this visualization, is one interpretation of the neural network here. I'm taking this grid here, and I'm showing how this space gets warped by the neural network. So you can interpret what the neural network is doing is it's using its hidden layer to transform your input data in such a way that the second hidden layer can come in with a linear classifier and classify your data. So here, you see that the neural network arranges your space. It warps it such that the second layer, which is really a linear classifier on top of the first layer, can put a plane through it. Okay? So it's warping the space so that you can put a plane through it and separate out the points. So let's look at this again. So okay, so you can roughly see how this gets warped so that you can linearly classify the data. This is something that people sometimes also refer to as kernel trick. It's changing your data representation to a space where it's linearly separable. Okay, now here's a question. If we'd like to separate, so right now we have 6 neurons here in the intermediate layer, and it allows us to separate out these data points. So you can see actually those 6 neurons roughly. You can see these lines here. Like they're kind of like these functions of one of these neurons. So here's a question for you. What is the minimum number of neurons for which this data set is separable with the neural network? Like if I wanted the neural network to correctly classify this, how many neurons do I need in the hidden layer as a minimum? 4? I heard some 3s, some 4s.
Binary search.
Binary search. So intuitively, the way this will work is, let's see 4. So what happens with 4 is there's one neuron here that went from this way to that way, this way to that way, this way to that way. There's 4 neurons that are cutting up this plane. And then there's an additional layer that's doing a weighted sum. So in fact, the lowest number here would be 3, which would work. So with 3 neurons, OK, it's going to happen. So 1 plane, 2nd plane, 3rd plane. So 3 linear functions with a nonlinearity. And then you can basically, with 3 lines, you can carve out the space so that the second layer can just combine them when their numbers are 1 and not 0.
Can we see what happens at 2?
At 2, certainly. So at 2, this will break because 2 lines are not enough. And suppose this works, I'm not going to look very good here. Yeah. So with 2, basically, it will find the optimal way of just using these 2 lines. They're kind of creating this tunnel, and that's the best you can do. Okay.
What causes the curve in the three neuron case? They don't have pointy ends.
The curve, I think, which nonlinearity am I using? 10H? Yeah, I'm not sure exactly how that works out. If I was using ReLU, I think there would be much. So ReLU is the. So let me change to ReLU, and I think you'd see sharper boundaries. Yeah.
With 3, you get like 4.
Yes, this is 3. You can do 4. So let's do.
But it's 3 right now, and you've got a bunch of lines.
Yeah, that's because it's because in some of these parts there's more than one of those ReLUs are active, and so you end up with. There are really 3 lines, I think like 1, 2, 3, but then in some of the corners, 2 ReLU neurons are active, and so these weights will add up. It's kind of funky. You have to think about it a bit. But OK, so let's look at, say, 20 here. So change to 20, so we have lots of space there. And let's look at different data sets, like, say, spiral. So you can see how this thing just, as I'm doing this update, it will just go in there and figure that out. Or very simple data set is not like a spiral, circle. Yeah, and then random. So random data, and so it kind of goes in there and it like covers up the green ones from the red ones. And yeah, and with fewer, say like 5. I'm going to break this now. It's not going to. Okay. So with 5. Yeah, so this will start working worse and worse because you don't have enough capacity to separate out this data. So you can play with this in your own free time. OK. And so as a summary, we arrange these neurons into neural networks into fully connected layers. We've looked at backprop and how this gets changed in computational graphs. And they're not really neural. And as we'll see soon, the bigger, the better. And we'll go into that a lot. I want to take questions before I end. Just sorry. Were there any questions? Go ahead.
Is it always better to have more neurons in the thin layer, or is there also like some kind of?
We have 2 more minutes. Sorry.
So is it always better to have more neurons in the thin layer, or is there also like overfitting issues?
Yeah. So thank you. So is it always better to have more neurons in your neural network? The answer to that is yes. More is always better. It's usually a computational constraint. So more will always work better, but then you have to be careful to regularize it properly. So the correct way to constrain your neural networks to not overfit your data is not by making the network smaller. The correct way to do it is to increase your regularization. So you always want to use as large of a network as you want, but then you have to make sure to properly regularize it. But most of the time, because computational reasons, you have a finite amount of time, you don't want to wait forever to train your networks, you'll use smaller ones for practical reasons. Question?
Do you regularize each layer equally?
Do you regularize each layer equally? Usually you do, as a simplification. Yeah. Most of the often when you see networks trained in practice, they will be regularized the same way throughout. But you don't have to necessarily. Go ahead.
Is there any value in using second derivatives and backpropagation?
Is there any value to using second derivatives, using the Hessian in optimizing neural networks? There is value sometimes when your data sets are small. You can use things like LBFGS, which I didn't go into too much, and that's a second order method. But usually the data sets are really large, and that's when LBFGS doesn't work very well. So when you have millions of data points, you can't do LBFGS for various reasons. Yeah, and LBFGS is not very good with mini batch. You always have to do full batch by default. Question?
What's the difference between having more neurons in your hidden layer versus just making the vector size bigger? So instead of 100, you can make 500?
So what is the trade-off between depth and size, roughly? Like, how do you allocate? Not a good answer for that, unfortunately. So you want depth is good, but maybe after like 10 layers, maybe if you have a simple data set, it's not really adding too much. We have 1 more minute, so I can still take some questions. You had a question for a while.
What happens if you change the number, like I guess the number of layers instead of the number of neurons?
Yeah, so the trade-off between where do I allocate my capacity? Do I want this to be deeper or do I want it to be wider? Not a very good answer to that.
So is it also true that it's better to have more layers as well? Or?
Yes, usually, especially with images, we find that more layers are critical. But sometimes when you have simple data sets like 2D or some other things, like depth is not as critical. And so it's kind of slightly data dependent. We had a question over there?
What happens if you use different activation functions for different layers? Does it help or?
Different activation functions for different layers. Does that help? Usually it's not done. Usually you just kind of pick one and go with it. So say for ComNets, for example, we'll see that most of them are trained just with ReLUs. And so you just use that throughout. And there's no real benefit to switching them around. People don't play with that too much. But in principle, there's nothing preventing you. So it is 4:20, so we're going to end here. But we'll see lots of more neural networks, so a lot of these questions, we'll go through them.